So again, this is one of the simplest summaries we can do. And then once I get that summary, I don't have repeated measures anymore. I just have the baseline covariates and the summary outcome, and then I can do what I would normally do without having to take this class. The only other thing you can add to this is when I do have different numbers of observations on a subject, I may want to weight subjects differently. If I have 30 blood pressure measurements on one subject, maybe their measurement of blood pressure should get higher weight than somebody that had 5 measurements, because I get a better estimate of it. And there's various ways you can weighting. Weighting is one of these things that has a theoretical property that it's always better to weight by the inverse of the variance of the outcome, asymptotically, as sample size grows. Of course, we never know the variance. We have to estimate the variance. So you don't weight by the variance, you weight by 1 over the variance. So if I have the variance of my y bar, I, for a particular subject, if I knew it, that would be a great weight. Of course, I don't know it because you don't know the variance. You have to estimate the variance for a subject. So you estimate their variance is the variance of the outcome over the number of observations. And if I do the inverse of that weight, in theory, that's the maximum likelihood estimator. That's the best one. But it turns out, whenever you estimate weights and you don't know them, you could have way more variability than not weighting. So you have to be. It's better to weight for something that's very stable than to weight by something that's could be unstable. And estimates of variance, if I have like 3 or 4 measurements, can be very unstable. It's a very messy weight. If I took a different 3 samples, I get a completely different weight. So you start weighting randomly, that just adds noise. It's just a lesson to learn in general when doing weighting. If you can do it by design or whatever, if you can avoid weighting, that's the best. But even when weighting makes sense, it's better to weight by something that you don't really have to estimate and it doesn't have a lot of variability. Because you put something in the denominator with a lot of variability, it can get really huge. Like I can, by chance, estimated variance is close to 0, that's going to be a huge weight when I put 1 over it. And I'm going to weight some subjects by 1,000 times. And so you start ending up getting regressions where like a few people dominate the estimate of the coefficients, and that's always unstable. So just be careful about using estimated weights such as 1 over the estimated variance of y bar I output. So one way in this case, I could just weight by the count. I don't have to estimate it. And of course that's related to the variance. It's not maximum likely anymore, but maybe a sensible weight, and that could do better, for instance, than having to incorporate also the estimate of the variance of the outcome itself, which is right. The variance estimate of y bar I is equal to s squared yi, which is a sample variance over ni. That's a sample. Oh, it's just something else that comes up. If I don't have regular measurements, if everyone's weight measured the same amount of time, it's not an issue. But if I get kind of irregular measurements and I want it, and I can also use weights, but I have to be careful about weights because they can really create more instability than they fix. Okay, I'll just skip that. So we have a quick example. I'll go very quickly. It's the HIV CD4 count example. And we'll look at baseline measure of some kind and look at repeated CD4 counts as our repeated outcomes. So again, it's the same data that we've looked at many times. Again, this is what it looks like originally. So I have to, first of all, I have to create some baseline covariate. It's not part of this data. So I'm going to choose, I think, viral load at the first time. I'm going to look at that impact of CD4 count over time. Again, this is, the general problem. I have longitudinal data. I need to make cross-sectional data. I want that. I have to create a baseline exposure from viral load. I have to summarize all the CD4 counts over time on each subject separately and create a new data set. That's all this is doing here. So it's always the nuisance in this course, and will be when you do your own analysis, that data processing becomes a big part of it. Data manipulation, data wrangling, whatever you want to call it. So I'm not going to go over this because, again, it's one way to do it. You could do it many different ways. This is a way that I created both this average outcome as well as the baseline. And I use this first command here, which says just make your first viral load measurement my explanatory variable. So I'm looking at baseline viral load and then the summary of the CD4 counts over time on the subject, comparing them. Not necessarily a bad thing here because there's no change in treatment here. So it is a legitimate comparison. I'm looking at how does that baseline viral load predict the response to treatment. And when you look at the data at the end, this is what it looks like. Now I have one row per person, right? I got my base time. I'd like that to be 0, not always 0. That's the first measurement I get on a subject. And then I get my base log viral load measurement, and then I get my average CD4, and I also get the number of measurements used for it. So you can see it varies, 26 the first row, 7 down here, etc. So maybe that weighting will be helpful in this case. Just doing what we always do. Now it's cross-sectional data. I just want to look at the pattern. I don't see a strong pattern. So here's the average CD4 count that's measured on about 500 subjects versus base viral load. You can see you have a lot of them at the base viral load was non-detectable, right? So that's a lot of those. Again, you may want to worry about that and model it in a different way. It looks like as base viral load gets higher, the average CD4 count over time may go down a little bit. Doesn't look like it's a strong relationship. And again, we've talked about this before, and that viral load is a very messy measurement. So if I had replicates of viral load at the first time, maybe that would be a better predictor, but I only get one. Now I have my data. Well, I can just fit a simple linear regression. So this is just a simple linear regression where now I have X. I don't have a J anymore. Xi would be that baseline log viral load. Yi is this average CD4 count. In this case, I'm not using weights at all. I use these kind of library Broom, if you haven't heard of it. It's a tidyverse command that takes regression output and makes it look better. So they have these lovely commands in tidyverse that just take all this crap that you get back from these output and just displays the simplest form of it. And that's all I'm using here. And it gives me my intercept. Here's my relationship. It's kind of in the direction I expect. So minus for one log to the base 10 change in viral load, so a tenfold increase in baseline viral load gives me a decrease of about 4 units in CD4 count. Not huge for CD4. And this I wish it wouldn't do this. I mean, this one's fine, but this should be 0.27. And p-value is not significant. So my underlying the null hypothesis that there's a relationship between baseline log viral load and average CD4 count would not be rejected in this case. Because you basically, in this case, the null hypothesis that beta 1 equals 0 is not rejected. All I did here is just add the fitted line you can see to the curve. So again, this was a smooth. So, no model, just smooth through the data. And here's our linear model fit. And it's not surprising that it's a very shallow drop. We don't see a significant relationship. Anyway, you can look at that. It just gives you the results. So one thing I want to mention, this is going to start getting us in the second part of the course, is that when I get my inference back from standard linear regression, it's making assumptions about the variance model, even without the repeated measures part. So correlation is not an issue. These are all independent subjects. Their outcomes, their significance are unrelated to each other. At least we're assuming that. So it's not that part. It's the fact that it's going to assume something about the variance model, which the default is that the variance is constant, right? That'll be the variance around this line. If I could draw is always the same. So constant variance assumption. Affects the standard error calculation. So when it calculates the standard error, it's actually based on a model. It's not model free. It's based on a model that the variance is constant. If the variance isn't constant, then that standard error can be biased, right? So there is a way, even without repeated measures, there's a way to account for the fact that your model may not be true in terms of your variance model. We'll talk a lot about it in the context of longitudinal data, but it's also true cross-sectional data. I just want to make that point here. Here's what a plot that looks like, would be a plot that would look like if you had constant variance, right? So it looks, the spread around the line is pretty equal. There's former tests of this. The fancy term is called homoscedastic. That's just constant variance, which I like much better. And if you look at it, if you look at the form of the coefficient estimates in linear regression, it has a closed form, meaning I can get my estimates by taking a bunch of numbers on the right and doing a mathematical operation and get it once. I don't have to iterate anything. It's a closed form solution, meaning I'll have my estimates on one side and my data on the other side. And there's a mix of the two. We get to other kinds of models that's not true, and you have to iterate to find the maximum likely solution. But in this case, it is. So I can just look at the form of the coefficient estimates, what it looks like, and I can derive the variance. And without, because I don't care that much about the math, this is what it looks like. I'm not going to derive it. It looks like this. So this is how we get our standard errors, right? Our standard errors of the beta hats come from the estimate of the variance So this is a P by P variance covariance matrix. It looks like if I have, let's say I have two coefficients, it'll look like this. It'll be variance of beta 0 hat, covariance of beta 0 hat, beta 1 hat. They're always and the variance of beta 1 hat. So this is the variance of beta hat. P is the number of coefficients, so it's 2 by 2. When you run a regression procedure, that's what's behind the scenes. That's what it calculates first, and it does that based on this analytic calculation. But the one thing these are all known things, right? Those are that's just my covariance, right, predictor, or my basis functions, really. So this matrix operation, don't worry about that, but it's all stuff that's known. It's just part of your data. This thing has to be estimated when I get my estimate, that sigma, which is the variance of the residual, or the variance of y given x, the same. So it has to estimate that, and you can estimate that in two ways. You can say, well, I'm not going to assume any model. That's called robust estimation standard error. Or you can say, no, I'm going to use the standard assumption, which is homoscedasticity or constant variance, and it ends up, you get this, right? So this is what it reduces to under this assumption. It now just has one parameter, which is the variance of the residuals, which you can get you can get an estimate of it by just looking at the residuals and get a sample variance, right? You multiply that by this function of the known data, and you get your estimate of that thing here. So that is the naive, what we would call the naive estimate. And naive is the same as model-based. In other words, I'm assuming it may be naive to assume this model, it may be wrong, right? That's what we call it naive. But we'll hear this term naive estimates of the variance, and that's what this is. Don't worry about the math. It's just going to make a strong assumption about the variance model by assuming every residual has the same variance, come from the same distribution with the same variance, and it simplifies the calculation. That's not important for this class. The important thing is that's underlying the assumptions when you get your estimates of your variance covariance for the coefficients. And then, of course, just to make this clear, like the standard error of beta hat 1 is equal to the square root of the estimated variance of beta 1 hat, right? So we never know the variances, we have to estimate them. We use this equation to estimate it, and what we do is we plug in estimates of the unknown things, which are just these things here. Either in the more general case, that big capital sigma, in the smaller case, in the naive model, it's some estimate of the residual variance, which is just in this case you would just use the sample variance of the residuals. Get the residuals from every subject, get the sample variance, plug it into this formula here, and you have your variance covariance, and then just grabs the diagonal of this thing, estimated one, and takes the square root to get the standard error. And that's what it puts in the output. So that's the whole process by which this regression and the post-regression estimate of the variance covariance of the coefficients leads to a standard error. And then you can get your confidence intervals and your p-values, et cetera. So when it's not true, the constant variance assumption, it may look like this. It's exaggerated, but here are the variance. It's often you can often see the case, particularly when you're dealing with things that are like counts, that the variance gets bigger as the mean gets bigger, right? And this, in this case, I don't know if this is realistic at all, but the variance is going bigger as the covariate gets bigger. And I just made a little simulation that did it. It's not important, but it's just an example of where that assumption of constant variance is going to go wrong. And therefore, if I assume it by just getting the standard results from a linear regression, I'm going to get biased standard errors, biased confidence intervals, et cetera, right? So assuming could lead to biased estimates of the standard error.
And does that bias estimate has a specific direction, or it can go?
No. No, there's nothing general to say about that. Yeah. I mean, it could be it's when you get your residual variance, it's averaging the residual variance here to here and here, and maybe just putting it in does a good enough job. I don't know. It doesn't even necessarily mean it's going to bias it. But in general, you rather get standard errors that don't rely on unnecessary assumptions, right? If you do diagnostics where you do apply the residuals versus like the mean and it looks constant, maybe you feel more comfortable with the naive standard errors. But in general, I would just say is you always go for the robust estimate of the standard error, because why make that assumption? If the assumption is true, the robust standard errors will go to the naive standard errors. as sample size grows. So it's not like you bias them by assuming robust if the naive is true. So it's just generally better to assume a bigger model when you're going to use standard errors, unless you have strong arguments for why the naive model is correct, and you almost never do. So robust standard errors, all they do is take that original formula that we put up here that you don't have to worry about, and they plug an estimate of that whole variance covariance. That's a diagonal matrix in this case, because remember it gives you the covariance of every observation, but they're all zero because of independent. So it just has something on a diagonal. They call this a sandwich estimator. So you may hear this, that this is a robust standard error estimates or robust variance in this matrix, but you get the robust standard errors from it. And they call that the sandwich estimator because you have this called the hat matrix on either side. That's the bread, and in the middle you have the estimate. So it's like you get, this just looks like that part. That's the bread. And that thing there is the cheese, or whatever you want to call. It has the sandwich form, and they call it the sandwich estimator. So that means you have to get a different estimate of this thing when you plug it in. It's not going to be just a constant variance now. We're not going to talk about how you get it at this point. We'll talk about that later, but some way of getting it that doesn't make the assumption that the variance constant. Let's just say that for now. Just to show you, because I didn't go over this, is what it looks like, right? If I have a variance, this thing, it's the variance of the first observation, second observation on the diagonal. If I had a sample size of 10, it would be a 10 by 10 matrix. If it was a sample size of 1,000, it'd be a 1,000 by 1,000 matrix. But all the off diagonals are zero in this case because I'm assuming independence. So again, the independence assumption, it's inherent when you fit the LM regression, but it's an assumption, right? And of course, if that's not true, then you're going to be, it's not estimating the covariance, it's just assuming they're zero. So you have to plug in some estimate of this thing when you, of these, and you could do it in various ways, and we'll talk about how to do it that assumes absolutely nothing. It assumes that every variance could be arbitrarily different. That's the most robust version. But there's other versions that may assume a little bit more than that. And I just give you an example of fitting it. So how I use this thing called sandwich, and that's for taking a regression and then using this to get your robust standard errors. This is what I would always recommend when you're doing even just standard regression. Always good to check this compared to the naive. Here I have the original one. Here's my estimate and my standard error. When I do the robust, I get this same estimate. The estimate doesn't change, even though one has decimals and the other one doesn't, because the estimates don't change. It doesn't change the estimates. It only changes the standard errors, and I can see I get a much bigger standard error here. That's liable to give you more accurate inference, p-values that are trustworthy, confidence intervals that have the right coverage, etc. So just an example, toy example, to show the importance of not necessarily defaulting to the standard errors you get back from typical regression. It's always a good idea to use a robust version. And I did this again. Don't worry about that. I redid it for this CD4 example. Actually, in this case, it's not that different, right? Here's the standard error here. Again, this is just rounding. They're identical. It's almost the same. Like, you're not always going to get big, but I know now they're the same. So then I don't have to worry about getting biased standard errors. I could use the naive because I've tested it, and it's the same as the robust. So if they're same, maybe that constant variance model works well enough in this case. Okay, I'm going to summarize the slide, and then that's just the weighted. Don't worry about the weighted. The weighted regression in this case for the CD4 count example might be worthwhile because there's so much variation in the numbers, and you don't want the same person to weight the same if they only contribute 2 observations to the average as opposed to 30. So it's a good, and again, the weighting makes, to me, more sense to use the number, which is not I don't have to do any estimation, than the classic one, which would be 1 over the estimated variance of the average, which has this additional noise element to it. But again, that's another kind of dual message that's general, not just for this course. Use robust inference. When in doubt, when you're using weights, be careful about estimated weights. And then next time we'll get into count, summarizing his counts and getting into count regression. I'll go pretty quickly because I don't think it's central to the course. I just think it's useful to have in the context of time invariant covariates. And so there's a lot of slides, but they're not, I'll try to highlight what's important and what we can ignore. Any last questions? Okay, see you on Thursday. Thank you. Hey, I'm going to skip over the few slides at the end with the weighted, where we weight by the number of observations. Everything's the same, essentially. All the coding, everything, except for you're adding a weight to the regression, and the LM has a weight option. And I went over why weighting by the number is probably a better idea than trying to weight by the inverse of the variance of the average for the subject. So again, just to emphasize, you don't need, when you're doing this or data reduction of all the outcomes, in this case we have only time invariant explanatory variables, you can choose different things. I mean, you can choose, one interesting thing would be, if I'm interested in a situation where I want to compare slopes, like are they increasing in CD4 count versus not? For some treatment at baseline, you could estimate a slope in each subject and do the same thing. You might weight by the number of observations used to estimate the slope. That would be your new outcome. You could do, if you have a multivariate outcome like we have, you could do principal components. That's a little harder to interpret. I'm not, we talked about that earlier. As a way to reduce the a multivariate observations to one or two numbers, depending on how many principal components, but it doesn't have an easy interpretation afterwards. Okay, now we're just going to talk about the rest of today when we have repeated binary counts over time on the subject. So events, counting the number of events, asthma attacks. We've talked about episodes of diarrhea or gastrointestinal distress. It could be you have a cutoff for CD4 count, which I think you're going to do in the lab. So the number of counts you get below a critical value of CD4 in the HIV case, et cetera. And so the same context here, it's just where we happen to have a variable where we can reduce to a count, and then that brings up how do you model counts. And that's a fairly big topic in itself, but I think I'm giving you in this lecture, for the most part, all you need to really know about it. Again, if you have time-dependent covariates, it doesn't make sense. You can't average the number of covariates over time versus the outcome over time, because then you have no idea what comes first. You don't know what you're mixing up before and after. You're going to get associations could have that whole time ordering goes away. So only relevant, again, if I have fixed baseline covariates. So again, I've repeated yes/no measurements on subjects. Again, it could be a design where I have regular measurements on everybody. It could be much more like the HIV design. CD4 count one, where we have very irregular measurements on subjects. Wait a minute, it's just the same thing, sorry. Okay, we'll look at this water intervention trial, which is that where we randomize at baseline. Again, just to remind you, a device that actually cleans the water, gets rid of all the pathogens. This is not a study about chemicals in the water, it's a study about pathogens in the water. And then they randomize either that or a sham device that looked just like the device that actually was functional, but it didn't have the mechanism to actually kill the viruses and the bacteria and other possible pathogens. And then daily, they were supposed to record whether or not they had a gastrointestinal event, right? So there could be a diarrhea one, could be vomiting. It's defined in this particular way that the WHO uses to define a gastrointestinal event that could be due to a pathogen. So we're not, in this case, some studies they actually measure, you get like stool samples or whatever, they actually measure whether you have evidence of pathogens, because you can have gastrointestinal events, particularly in this population, that are due to things like medication, which of course you can't prevent by drinking cleaner water. But that wasn't true here. We only had diarrhea that they recorded. And again, people didn't record every day. There's different numbers of observations per person. And so we want to look at the amount of GI illness attributable to drinking water. And again, just to remind you, this was a type of study that was very popular for a while that was trying to get the burden of disease caused by drinking water with pathogens in it. This was in San Francisco, which has actually pretty clean water. The source water is pretty clean. And the system that delivers it, I think, at least at the time, was pretty clean. You can go to other places where the water does have sources of bacteria and viruses in it. Often that's really true with well water. So unregulated well water is often a source of GI illness in subjects. In fact, I'm involved in a trial putting water cleaning devices in Appalachia, where lots of people are isolated houses and they have well water. Again, this is what the data looked like. We had, the outcome, it's just a 0 or 1. We had the group therein, filtered or non-filtered. We had the study day and the ID. So it's in that repeated measure structure. Again, it was the HIV wet study. And of course, we have to reduce that to 1 line per subject, where we get whether or not they got a certain device and how many events they had and how many days they reported, right? Because if you only reported 4 days and had 4 events, that's very different if you had reported 100 days and had 4 events. So we'll have to incorporate that in our analysis. So nothing terribly magical here. We're going to create a new outcome, yi, which is just the sum of all the y's. Remember, it's a 1 if it occurred, a 0 otherwise, so the total number of 1s will give you, for every subject, the number of events. And of course, we'll also know the NI, the number of time they actually reported whether or not they had an event. So again, you're hopefully getting a fair amount of practice of this, looking at a lecture and lab at how, take a data set like this and you do your data wrangling, in this case using dplyr. We've also talked about data table. And at the end, when you do this, you get the total number. This is really your NI, and this becomes your new YI, right? So it's the total number of times you reported, and then how many events you reported. So the first person reported no events for the 111 days that they filled in their diary. You can see it's pretty consistent. Most people fill it in daily, but there are some people that don't. So it's not perfectly balanced data. Okay, so there are certain distributions of counts. Now, again, when we're interested in how the mean changes of counts when we are looking at 2 groups or we have other covariates to explain them, we ultimately can estimate things, maybe not even caring about the distribution of the counts, but a kind of default method people use is called Poisson regression to look at this, and so they're assuming the Poisson distribution for the count. So conditional on being in a group, you have a certain Poisson distribution. This is what it looks like, right? Where little y goes 0, 1, up to potentially infinity. For all, anytime you deal with these kind of distributions, parametric distributions, meaning they're just defined by 1 or 2, or a finite set of parameters. In this case, it only needs 1 parameter to define the whole distribution. Once I know lambda, I can give you the probability of any number of events, any number of any count. And yeah, so this is the form of it. It can be derived in some ways from first principles. For instance, if you have exponential survival time, at the time to event, an event is exponential. You can, and then you reset and go to another one. You can derive that the number of counts over a block of time would be Poisson. So if you're like 201A and B, if you're a biostat student, you probably did an exercise like this where you compared how these different distributions relate to each other. We're not doing that in this class, but that's a common sort of introductory graduate student kind of exercise. And then finally, just if you don't know, when you say y explanation point, that's y factorial. So it's y times y minus 1 all the way to 1. So again, you only need to know this one. Once I know that, I've got my whole distribution. With normal, all you need to know is the mean and the variance. So it's a 2-parameter family. This is a 1-parameter family. And obviously, when we get to modeling it, we're going to model the parameter lambda as a function of covariance. That's the way you look at these things. And we do in the normal case, we model the mean, the 1 parameter, as a function of covariance. So at that point, we add other parameters because we're adding the regression coefficients, which we'll do here. Sometimes they call this the rate of events. It's often used for things like rates. It's commonly used, and we'll go over that in a sec. It's used in many different contexts of Poisson as a way to model counts of events like earthquakes, et cetera. And because you only have to estimate one parameter to get it, and that parameter turns out to be the mean, it's also the variance, you have relatively easy like substitution ways to estimate it. If I want to estimate lambda for a certain if I get a bunch of counts on different subjects, for instance, I want to estimate lambda. Obviously, if I do the average, that's an estimate of lambda, right? I just take the mean, the empirical mean of y, and that will be lambda. So again, you'll find this used a lot in the literature because it's so convenient. Some of the places it's used quite a bit, things like automobile fatalities in a given year, region over a year. It's often used in cancer case, looking for hot spots. So they'll do like this thing where they'll compare, for instance, like the lambda in a particular region, the number of counts of cancer versus as you get bigger and bigger, does lambda get smaller and smaller? It could be, they call these hotspot investigations. And they often use Poisson distribution to describe that. Again, in this case, there's no covariance. We're just trying to describe a distribution of counts. This, of course, when you hear a probability of having a certain size of earthquake, that's also based on Poisson often. So you can get Poisson counts of different magnitudes. Again, you could make it a function of magnitude, and then you could get some idea of how many, what's the probability of having one or more in the next 30 years, and that's kind of what you hear when you hear these forecasts. So they use the historical record, get counts of earthquakes of different sizes, and then can use the Poisson to sort of give you a probability of what's going to happen in the next 30 years. It can get much more complicated than that, but that's sort of the basic idea. Also, you can use it in the context where you have event processes, things that occur only once. But as I said, it has a constant rate of hazard, which is exponential. Don't worry about that, so don't worry about this. It's just another place it's often used. So in some things you can derive that the distribution is Poisson from first principles. We don't have that very often in public health. We can't say, the theory should tell us that something should have a certain distribution, but that's not true in Poisson. You can, if it has a constant rate of hazard, and you can show that something has a constant rate of hazard. One famous example is radioactive decay, right? When you hear the little Geiger counters that are counting radioactive particles emitted, that has a perfect Poisson distribution. So there are things where actually, it's one of those things where you actually have physical principles with theory that lead you to know what the distribution is. That's very uncommon for us. We often use these as distributions of convenience because we have a count, it'll work for counts, may not work perfectly, which we'll see. But in some cases, you can derive them from first principles at the distribution. Again, what's another place where we can derive this super important statistics where we can derive the distribution from first principles? The most important one.
Normal distribution? Normal distribution?
And how we derive it from first principles? Averages, right? Averages go to normal distributions. So you can show that in theory, right? That's the basis of much of our inference. As the sample size gets larger, an average will have a normal sampling distribution. So that's another one. That one's also true. And that one, of course, we use, if we're doing data analysis almost daily. So when everybody has the same time or repeated measures that they record, it's pretty straightforward. You don't have to worry about the time period because they're all the same. When it's not, so people might, we follow for 10 days or 100 days or 1,000 days, and we want to account for that. The Poisson has a very natural way to account for it. So if something's Poisson, let's say y, with lambda, that's per unit, whatever that unit is, day, year, whatever. It turns out if I want to look at a multiple of that unit, 5 years, 6 years, then the rate it becomes Poisson, where it's just that time period I'm looking at times lambda. So and this will actually come into how we model it when we start doing more complicated regression models. So a Poisson, if I have y is Poisson lambda per year, and I want to know what's the distribution of counts in 5 years, it's Poisson with 5 times lambda as my new lambda. So just a simple example. If I have an accident rate in a town, which is 0.000024 per person per year, lambda always has units, right? You can't just say lambda. You have to specify what it's measured over. Then in a town of 1,000 people, I just simply multiply it together, and I get 2.4 in that town per year. If this was my per unit, per person rate, then I can get a rate for everybody in the town. Same year, so that doesn't change. If I just take that count and just look at, okay, what's the probability of having no events in the year? So this is why it's very useful, because I can take a few years, get an estimate of lambda, and then I can project, okay, what's the probability I get 0? Is 0 unusual? Is it a low probability given the past? And of course, I can just plug and chug by plugging y, which is in this case 0, and lambda, which is minus 2.4 in the equation. I can get, okay, if I have a 10% of the years in this town, I expect to have roughly 10%. I expect to have no fatalities by accidents, and then I expect to have 21% of the years, or 22. I would expect to have 1, and then the probability to have more than 1, of course, is just 1 minus the probability of 0 minus the probability of 1. So that's probably having any more than 1 is going to be 70%. So anyway, you can see how this would work in the cancer prediction thing. You get rates of cancer in some standardized population, and then you go to this and you say, how unlikely would this have been if that was truly the rate? And if the rate's higher, you start doing, in some cases, an investigation of the source. And there's famous examples that they've written books about, et cetera. But often this is the type of evidence that's often used. What does the distribution look like? It looks different depending on lambda. So this is we're 2.4. I'm using the same one. And this just gives you, it's discrete distribution. So it doesn't make this sense to say what's the probability of y equals 1.2. You don't look at equals 0, 1, 2. It's a count, right? So each of these, it's not really a histogram. It's kind of like a bar, which tells you the probability of each number of events. It peaks at the, close to the mean. That's 2. 1, etc. And then it often has this kind of tail that dies off quickly. Obviously, as you move the mean up, it moves to the right. If the mean gets big enough, it'll start looking symmetric, like a normal. And in fact, that's another classic exercise you do in sort of a beginning stat class where beginning theory is you'll start approximating Poissons with normal distributions, and you can do that. Because you have the variance, you have the mean, that's all you need for the normal. If it's symmetric, it may give you a good approximation to a normal to the Poisson. I don't know why you want to do that, because you can just do the Poisson, but anyway. When you only had lookup tables for the normal in the back of your textbooks, you didn't have computers, which was, the way I started. You had to convert everything to, you want to approximate everything with a normal, because I could always look it up in the table, but, now that this is really not an issue. So you can show, it's pretty easy to show that if I do maximum likelihood. So, I'm doing if I have the likelihood, and I'll say of the data, so I have I'll just say one observation, and lambda, it's just the probability, right? It's e to the, no, it's y to the lambda. I always get this wrong. Yeah, it's e to the lambda to the y over y factorial. Did I get that right? Or is it minus lambda? Minus lambda. So that's for one observation, the whole likelihood for all observations. So I'll put L and then Y. If they're independent, again, will be I equals 1 to m, e to the minus lambda, lambda to the yi over yi factorial. So this is your likelihood. You take the log of it. You take the log of it. You usually try to maximize the log likelihood, because you have something that's a product. If I take the log of it, it's a sum, so much easier to. And log likelihoods have nice behavior because they're like sums, so and they're concave. With respect to lambda, you can take the first derivative of that log likelihood. That's how you find the maximum, right? And you're trying to maximize the likelihood. That's what MLE is. So you get something like, a plot where you have lambda here, and then you have the log. Log likelihood is often a small l, but like this, and you get something like that, and you find the maximum, and that's your lambda hat MLE. That's your estimate. This right here is the log likelihood. So, we're going to do a fair amount of log likelihood analysis. We're not always going to worry about what the likelihood looks like. We'll get more, sometimes we're just going to be more into the practical application, but this is the basis of it. So in this case, it's just a one-dimensional plot of the log likelihood. And in this case, it's a very easy likelihood, nice and concave. It has a clear peak. That peak you can find analytically in this case. So if I took the derivative of the log of this thing with respect to lambda and set to 0, which is how you can solve a concave function, because the slope right here is 0. So I want to know what is the where is the slope 0? So I set it to 0, and the slope, of course, is the derivative with respect to lambda. And then I solve for lambda. You'll just see that lambda turns out to be the average. So it's very intuitive. We already know if I took the mean of a random variable with respect to this distribution, it would be equal to lambda. You can work that out too. That will involve an infinite series, but it's not terrible to figure out mathematically. And so that's how it's done. And that'll be how it's done. And it gets more complicated, of course, when we get to things like we're trying to model lambda as a function of covariates, but the process is just the same. It's just that now we have maybe two coefficients, so our likelihood is a surface in 2 dimensions, right? And we have to find the peak in more like a hill. In 3 dimensions you can't picture, but that's how it's done. this comes to the idea of like proper model. So if I'm going to model lambda as a function of covariance, so now I want the covariance to determine what Poisson a person has. If they're, you know, if they're 70 versus 50, if they're certain SES, if there are combinations of them, the natural thing in this case is to model lambda, because it's the mean, as a function of covariance. But we want the whatever regression model we're going to use, we want it to be proper, meaning no matter what I put in covariance and coefficients, I want the mean to stay within its proper bounds. And we know it can't be less than 0, right? Because the mean has to be positive. It's all the mean of positive counts. It doesn't have an upper bound in this case, because the Poisson goes to infinity. I mean, the Poisson goes pretty quickly in the tail, so it never really goes to infinity. It probably is get infinitesimally small pretty quickly, but it kind of goes to infinity. There's a positive probability of having an infinite count. If I model as a linear function, I don't have that guarantee, because I can get a negative value if I put, you know, a big negative coefficient and a big positive coefficient, a big negative predictor, I can get a negative number, and that would predict the mean is negative, and that won't work. So the way to make sure that never happens is to use the right link function, and in this case, the link function is going to be the log. So we're going to, the log of lambda x, just taking this and taking the log, both sides, which is the log of the mean of y given x is beta 0 plus beta 1 x. And that guarantees no matter what I put here, that can go from negative infinity to infinity, but once I exponentiate it, it can only go from 0 to infinity. So it's a proper model for counts. And that's why when you do count regressions, and you say, I believe my distribution is Poisson, maybe using a GLM or other procedure, well, you'll use a GLM, it will automatically do a log linear model. So it's kind of like, it's very similar to like logistic regression, which is not log linear, that's logit linear. But in fact, you'll see the way we get interpolate coefficients is very similar. So that's why we model the log rate, not the rate, as a linear model. I should put as a linear model. And it turns out that that's actually pretty important. You can, as I mentioned earlier, you can fit improper models, and sometimes, if it works, they're great. For instance, a log linear model you can fit with binary outcome data, which doesn't guarantee that the predicted probability won't be greater than 1. But if your event's pretty rare, maybe that doesn't happen. And then you get regression coefficients that have a different interpretation from log odds ratios. Then they become log relative risk. But in general, you can gain a fair amount of efficiency by using a proper model. And in fact, it's not, I don't teach this much in this course, but if I knew I had an upper bound, Poisson doesn't assume there's any upper bound to the count, but if I know the most I can get is 100, incorporating that is also very useful. And there's ways to do that, where you do a distribution that doesn't allow a count that's greater than 100. You have to do a different kind of transformation, but it's always good to try to fit proper models that really respect what you know about the random variable, and particularly when you have small sample sizes, that can gain you a lot of efficiency, so lower variance. So again, just doing the kind of annoying algebra to try in this very simple model where x is binary. It's either, let's say, exposed or filtered water, unfiltered water. I just plug and chug, so if I put 0 in the model for x, I get, that's the mean when y is 0 or lambda 0. I get e to the beta 0, so e to the beta 0 represents the mean when x is 0. When x is 1, of course, it's beta 0 plus beta 1 times 1 or just beta 1. If I take the difference of the log of the mean when you're 1 and the log of the mean when you're 0, I get this log ratio. And so that's, whenever I get a log of something that's interesting, and this is interesting, this is a ratio of means, right? Of means or or sometimes they'll call them rates. That's a rate ratio. It's kind of like a relative risk. Meaning if I get a coefficient that has that interpretation, all I have to do is take the inverse log or exponentiate it, and I get a relative means. I get a ratio of means, which is often called an incident rate ratio. So much like logistic regression, when you exponentiate the coefficients, let's say on an x, if it was a logistic regression, I get an odds ratio. In this case, I get a rate ratio. That's what it's called. It's the ratio of means. All the other things we talked about regression, where I have more complicated things, so I have interactions and quadratic terms, you do the same process we did there to try to figure out the associations of interest in terms of functions of the coefficients, and we can use those commands we learned in R to get back the estimates and the inference for them. So nothing changes. All regressions have this form, parametric regression. So once you learn it for one, you've learned it for all of them. Where you just have to remember, sometimes you have to exponentiate and sometimes you don't. Linear case you don't. Poisson, logistic, you do. This is also not rocket science. If I know the estimate of lambda, the maximum likely estimate is just the average. It means that I can get the average for lambda 0. That'll give me, among the x's that are 0, I get their mean y, average y. Among the x's of 1, I get their average y. And then I can use both of those to figure out what is the estimate of these coefficients. So you could do this by hand if you had to. You won't, right? Because you'll use something like Poisson regression, and it will do it for you. But the maximum likely estimate would look like this. It's just the average of y's when x is 0, and this is the average. That's all it is. So again, I know this was the log of the average when x is 0. So I take the log of that number that I estimated right from the data, I get beta 0. And oops, this is beta 1. Sorry about that. Beta 1 hat, which is just going to be the log, the difference in those two logs. Remember, the difference in logs is the log of the ratio. So it's a log. I could rewrite this. I just plug these numbers in, take the log, and that would give me an estimate of beta 1. And again, so also kind of a classic basic stat problem where they may give you a set of means for different subgroups and say calculate what would be the coefficients. And you can do that. This is called it's a simple model, but it's called a saturated model. Meaning I get a coefficient for every group defined by the x's, right? So I would get my estimates by just taking the mean of the outcome for every x value, and then I can connect them as a coefficient. So I could do this if x had 3 levels, 4 levels, and I treated it as a categorical. It would have the same story. If I had, just to make sure you understand a saturated model, if I had 2 x's, and they were both binary, x1 was binary, x2 is binary, it would mean there's how many groups defined by those 2 variables? 4. There's 0, 0, 1, 0, 0, 1, and 1, 1. And I get the mean of the outcome for all those groups, and that would define my mean, my regression of y given x. So whatever combination of values that I could get the estimate by averages. Every time I can get the estimate just by taking averages of outcomes within groups, that's called a saturated model. So again, you don't have to do it by hand. You can use the thing, but it means you're not assuming any relationship. I'm not assuming. I'm not assuming a slope or anything. I'm just estimating them non-parametrically. And again, just to remind you, if I have I have several x's, and I have, many values for each, possible values for each x, and I create the number of groups. The number of groups could be the number of people. There's no ties given those. And then, of course, you can't do this anymore then. You get one observation per group, and that's when we start modeling. We have to do some kind of simplification of the model, some kind of smoothing in order to get a realistic fit. So we may assume a linear, if x goes from 0 to 10, we may assume the mean changes linearly with that x, et cetera. So, and that's, of course, if we don't have to model, we just typically would avoid it because it always adds a bias when you're assuming a model. But often, with observational data and many covariates, that's often never possible. So we start assuming something smoother. Finally, if you look at, if I did the maximum likely estimate where you have actually different numbers of follow-up time, I'm calling that T now. So it's just sort of, T for us is going to be the number of times they were recorded, let's say, but it could be just the amount of time you followed them. It doesn't have to be an integer in this case. In general, it could be 1.2 years or whatever. It's simply the number of events over the total time. So you get like a per time unit estimate of the rate. And it's also easy to show with max. You could just define the likelihood. Now it's the likelihood is a function of lambda times t. Put that in. T's known, right? And of course the account's known. You optimize that likelihood with respect to lambda. That is, you solve the log likelihood, maximize it, and you'll get this function here. So this is also an MLE, maximum likelihood estimate. Okay, so now we'll just apply this to the HIV wet trial data that we talked about. In this case, our T's do differ. We have some people recorded at different numbers of days. Again, we're ignoring the fact that infinity is impossible here because we only follow them a certain number of days. You could use a different model to estimate this. Poisson's often used in this context. It's really kind of binomial because every day is kind of yes, no. And I have a certain fixed number of days, so I could do this with a binomial. But Poisson's often a good approximation to that, so we'll just use Poisson in this case for that. So again, this will be our model. We're going to have to, that's per unit, but this is our model given the number of times you were called, so this would be a per day. And this is, per period of time. Followed. Now when I take the log of this model, I get the log of t plus this. So it turns out, we haven't talked about this concept, but this introduces the concept of an offset. So when I do this, I see the model is a function, of course, x through this linear case, and then it has this thing here, which is kind of like a covariate. It just has coefficient 1, right? So an offset is something you put in there that you assume doesn't have a coefficient in front of it. And you can do this, if I have a binomial and I have lots of, I have the number of events per the number of times I flip a coin, I could do the same thing. But it can be used for other more clever uses. So offsets are something that you specify in the regression when you set these up for Poisson. So you don't put t in as a covariate, you have to put it in as an offset. Specifically, the log of t, the log of the number of times. They filled in the diary in our case, or the log of the time they were followed. So this is generally called an offset. It just has this special property that it's a covariate you put in the regression, and whatever kind of link you're using, in this case log link, that has the property that you don't estimate the coefficient. So you can still define the likelihood, it's just that it doesn't add a parameter to it. I'll just say, you can add a coefficient there. You can just put it as a covariate, the log of the time, and it just makes the model a little bit more flexible, right? It doesn't have to be 1 anymore. So that wouldn't be strictly Poisson, it'd be some other kind of distribution, but, so anytime I can add an offset, I could just add it as covariate. But in this case, we're gonna take the Poisson seriously and treat it as an offset. Okay, again, this was our data. And then, again, number of events, and what I call the YI, and this is what we call the TI. And so there's ways you can just summarize it. I'm just looking now at here, I'm using that, dplyr commands to get a summary. So I get total number of events, number of subjects. So this is number of subjects in each group. You can see it's a small study. So 21 got filtered, 24 got unfiltered, meaning they got a sham device. Total number of events in each group. There's a summary over all the subjects, all the times. Total time followed in the two groups. So it just summarizes all the times they filled in their diary in the filtered versus the unfiltered. You divide one by the other and you get a rate, right? So it's kind of our rate in one group versus the rate in the other, the lambda in the two groups. So pretty close, a little bit higher in the unfiltered than the filtered. Of course, we thought the filtered would cut you would think a priori, everything being equal, that it would cut the rate of gastrointestinal events, but obviously it didn't cut it much. So that's a typical summary you get when you have counts, and I'm comparing just two groups, is you do this kind of summarize the total number of people, total number of events, total time, and then and the groups, and then you can divide those two to get the underlying lambda, or the rate in the two groups. I can also just run this thing. So here you'll see here's my outcome, that's the count. I'll make this bigger. Here's my binary group, filtered versus unfiltered, and then I have this offset that you put. You just add and you put offset, and you put in what the offset should be, which is the log of the total number of times they filled in the diary in this case, and then you put family Poisson. So here's where it has this open parenthesis. You don't have to put that there, but that's where you can mess around. You can put a different link that doesn't use the default link, which is going to be log in this case, as we discussed. But in this case, you rarely do anything else besides just keeping the default. And now you get your estimate. So this is like our, this is our beta 0 hat, and here's our beta 1 hat. And then we get a p-value of the test that beta 1 hat is 0, and it's got a 0.781. So meaning in this analysis, it looks like the rate's about the same in the two groups. Retrospect, not surprising, because the fact that water probably isn't a huge contributor to diarrheal disease, and in fact, in this case, in this particular error, the HIV treatment drugs caused a lot of gastrointestinal stress. So you had this background, very high rate, but it wasn't caused by water. So it's hard to distinguish due to pathogens. Again, I can use Lincom to get my incident rate ratio, and you can see that number, the coefficient was close to 0, so the estimates close to this. I'm using unfiltered, so it says it's 1.0, the ratio of mean of unfiltered over filtered is 1.02. So in other words, it's slightly higher, but insignificant. And again, the p-value would be the same, because it's based on the same coefficient. I only have one coefficient of interest here. For those that don't have a lot of experience in Markdown, but are going to do a lot of analyses and want to keep a record of them, this is one of the great features is you can embed results in text. So I didn't do a very nice job here. I would round these and stuff, but these are not numbers I'm typing in. You'll look in our Markdown, and I'm referencing a result that's in the code block, so you can automatically create these documents that will spit out like a report and do the analysis and even have the text surrounding the results for the analysis, how you put them on. So if you're interested, look at our Markdown file for that. So there's something about the Poisson distribution, which is a real big assumption, which is assumes that the variance is equal to the mean. In this case, the mean varies by a function of x, but it assumes the same. Now, that's a big assumption, right? And you'll often see with public health data that that's not a very good assumption. And this assumption affects the estimate at some level, but it really affects the inference, right? Remember we talked about the variance model affecting the standard errors that you get, and this is a really big assumption. You can think, one way to think about Poisson is assumes that everybody with the same covariates has the exact same rate. It doesn't allow any variability in them, the model. So it assumes everybody in the filter group has the same underlying rate of the disease, of the outcome, as in that group. It can be different than the other group, but they have to be all the same within their group. And of course, that's a big assumption because we know people have different rates, underlying rates. People on different medications, they just have different gastrointestinal distress at baseline. So it would make it seem like a pretty big assumption that could really affect the inference, and you'll often see that. So in general, Poisson can be a very big assumption when you're fitting Poisson regression, and that assumption can really bias your inference, can make your standard errors way too small. And so we're going to learn a generalization of Poisson that allows a little bit bigger model. So it allows the rate of people within that group defined by the covariates to actually differ among themselves some, which is more realistic. So just note, you can always do something. So you can always estimate your coefficients and then use another method to get your standard error, which doesn't rely on the Poisson assumption. One we'll talk about somewhat in more detail later, but there's one that is a very non-parametric way to get your standard errors. It's not assuming any particular distribution, and it's based on resampling called the bootstrap, right? So I could do the non-parametric bootstrap here by just randomly sampling data with replacement, running my regression, getting my coefficients and storing them, and doing that like 1,000 times. So I get, let's say, 1,000 slopes. And that mimics, in some context, it works under assumptions, but under assumptions, that variation I see among that random resampling with replacement is what I would see if I went out and actually did a new study, which is what we're trying to mimic, the sampling distribution. So you get an estimate of the sampling distribution directly from the bootstrap, but it's not assuming anything in particular about the underlying distribution of the data. It's just saying, I have an algorithm, I apply it, it gives me back an estimate. What happens if I reapply that algorithm to a new study? That's what it's mimicking, and that is a definition of a sampling distribution. And so you can always get your standard errors that way, and they'll often differ quite dramatically than those that are based on the naive standard errors that are based on the Poisson assumption. So there's other ways to get it, and we'll learn, but a lot of this course is about robust inference. That is robust. And generally, it ignores distributional assumptions. Implicit in original estimator, like a regression. As I mentioned last time, always probably better. Oftentimes it won't matter that much. Doesn't necessarily matter that much in linear regression typically, but in things like Poisson, it can matter a lot because it's a much bigger assumption. So what's a generalization of the Poisson? There is a distribution that has one more parameter than Poisson, and there's several ways to motivate it. I'll only motivate it one way. In some ways, it doesn't matter. It's just it allows more variance than the Poisson does. It's called the negative binomial regression. So it's another option. It turns out it's not part of GLM. Typically, you have to load another package to use it. But in many ways, it's very similar. It has a similar model it models the mean, just like the Poisson. and it models as a log linear model, so the coefficients mean the same thing and everything. It's going to allow for greater variability than just Poisson. So you can have people differ in their underlying rates within the same group. Generally more conservative. Poisson's a submodel of it. So I can make a negative binomial look like a Poisson by turning one of the parameters to 0. And that, so it's a, Poisson is a submodel. I'm not going to go over this. You can. It's originally was motivated by coin flip experiments, so it only was relevant to discrete situations where I have a number of coin flip experiments, where some of these parameters result or only can be integers, but that's not generally the case. So you can read this if you want, but you can motivate it by a certain kind of flipping coin experiment. Where you like the number of heads, you say I'm going to fix the number of heads I need to get, and I'm going to count the number of tails that it takes to get that many heads in flips. That's basically it's an experiment like that. So I just think it's of historical interest, and that I don't expect you to remember this for the class. So you can kind of ignore this. This is the more interesting one and the more practical one for us. You can motivate it differently by assuming that subjects when all subjects within the same covariates have the same underlying rate. That's the Poisson assumption. If I can just say, well, I believe that there's some distribution of rates within the same covariate group, and that distribution has a certain form. Again, it will be a positive distribution because rates have to be positive. And I work out the math then. So I have this convolution of the rate, and everybody has their own Poisson distribution. They generate K's according to their Poisson with their lambda, but their lambdas can vary, and it varies according to some distribution. You can, if you choose the right distribution, you can do the math, and you end up with a negative binomial. So it just basically allows variability of counts of rates within covariate subgroups, which is much more realistic for health. Like, we don't measure everything about a person such that everybody in that group defined by those covariates should have the same rate. There's always additional variability. So it's a much more realistic distribution. And I'll give the specifics right here. So, I mean, if you care about the math, so if I assume that given you have a certain rate, then I'm calling this capital delta I. Is that capital delta? Yeah, right?
Yeah, it is capital.
I think so. Lambda, I'm sorry, capital lambda. It's capital lambda, I think. It's like a random variable, so I don't measure it. This is another example of a latent variable model. So it's a way to derive a model based on the latent variable that everybody has their own Poisson, and I don't actually measure what their underlying rate is, but I'm going to assume that their rate comes from a population where the mean rate is like a lambda. That's the new parameter of interest. It's not the rate, it's the mean rate. And these come from a so-called gamma distribution. So it adds other parameters. We still have the same lambda there, but now we have this other new parameter, which is it's defined as a gamma distribution. This is a positive. So if I look at a gamma distribution, so it'll be like here, and it'll be some positive thing, starts at 0 and has a tail kind of thing. So I can change that form of it by changing this parameter here. And again, the math is not terribly important for this class, but that's what it's assuming. And I put those two together, and I want to get just the probability of y itself. I have to get the probability that you're a particular yi, then integrate over all possible, capital lambda I. Then I have to integrate over all possible lambda i's according to this continuous distribution, and that will give me my marginal distribution, the thing that I would define my likelihood, and that turns out to be a negative binomial. which looks like this. So again, it's a count distribution. It's more complicated. It only has two parameters. This one has an original one, lambda, and it has this other thing, which they call the dispersion, but it's another parameter. This thing is called the gamma function. It's more general than if x is a count, y is a count, but in this case it is a count because it's for this, but not for this. So it's a more general definition, but if you have an integer here, it turns out it's 1 minus that integer factorial. Again, completely esoteric answer. It's not important at all for the course, but that's what the definition of that gamma function is. Again, we have the same mean. So the mean, if I only have a single outcome, I'm not talking about covariates. The mean's going to be lambda, so that's just like Poisson. But the variance is going to be lambda like Poisson plus this part, which is lambda squared over that dispersion parameter. And you can derive this way, but don't worry about it. Anyway, it's just a way to derive the variance when looking at the variance of the mean of y given lambda plus the expectation of the variance of y given lambda. That's a classic stat result, chain result. And you end up getting this. So that's how that's the variance. You can see it's going to be bigger than Poisson because this is Poisson and that's always positive. So it'll be bigger. So it allows more variability. It can never be smaller, the variance from a negative binomial. So in some ways it's a little restrictive. It would be nice to have one that could be smaller or bigger, but this can only be bigger. So it's always going to be conservative relative to Poisson. It's always going to give you conservative inference. It's going to assume the variability is greater than Poisson. And generally, that's probably better. You don't want to underestimate the size of your confidence intervals. And again, this is referred to as the dispersion parameter. You can see as this thing goes to infinity, then this term, here, let me erase this. As lambda goes to infinity, then the variance of y goes to lambda, which is Poisson, right? So in other words, I can make it look like Poisson if this dispersion parameter gets really big, or if I decide to parameterize of 1 over the dispersion parameter, sometimes you'll see alpha, which is equal to 1 over, if that goes to 0, then the negative binomial goes to Poisson. So also, it doesn't, if your model says Poisson's a good fit, you don't lose anything because your negative binomial will go to a Poisson. So it's not risky to try it because you're overestimating the variance. It's never going to be smaller than Poisson, but it can go to the Poisson. Only the class I care about is this one here. I don't care if you memorize the formula, but really just to know what the mean and the variance is in terms of those parameters, the dispersion and the mean lambda parameter. Don't worry about the other one. This is just a summary, because these two motivations have two different parameterizations, so this is how they relate to each other. Don't worry about that. We really only care. This is what they look like, the negative binomial for different, these all have the same lambda. They just have different dispersion parameters. So they go from very small, and that will mean you're dividing that lambda squared by a small number, so the variance gets much bigger. And those have the property that they start really high, but they have a really big tail. So this orange one has a lot of zeros, but then a lot of the total number of events are clustered at the very high end. And as it gets bigger, it looks more like Poisson, which is going to be a little more symmetric. So this one is essentially Poisson with the same. They all have the same mean. So all have same lambda. And the Poisson, the negative binomial is often a good distribution for modeling things that have a big right tail. That's often used for that. So if you have, let's say you're looking at one famous example is secondary cases from an index case in infectious disease. It's been used a lot in that context, where you have, let's say most people by far most people only infect one other person, or maybe no other people, or two other people. But a few people affect hundreds of people, these super spreaders. That's more like a Poisson, negative binomial distribution. It's widely dispersed, so you have most people very small, but they have this big right tail that really dominates the outbreak, how the virus or whatever it is spreads. So it's been used a lot in infectious disease. And you can estimate these two parameters. You can say something, combine it with an infectious disease model, and say something about how you expected the future of this disease to spread and when it should start declining, this kind of thing. So there are some diseases that look more like Poisson, and there's some diseases that look much more like negative binomial, that big right tail. So example of the latter would be things like SARS. SARS was an outbreak where most people didn't affect that many people, but a few people affect tons of people, super spreaders, and then you get this more negative binomial pattern. So if you get this count of secondary cases by a subject, you can estimate these parameters, and it gives you some insight into the dynamics of the disease. I think I have a paper on that's accessible on B courses that talks about this, and it's really not central to the course, but it's of interest to me at least. So you can think you're always more unbiased in terms of the distribution because it's a bigger model, right? Every time you make a model bigger, you're going to have less bias if they're nested. And they're nested because I can turn the negative binomial and the Poisson by setting one of its parameters to some value. In this case, the dispersion to an infinity. So anytime you make a model bigger, it's more flexible, and therefore it's more likely, has more chance to pick up the two distribution, right? That's just a standard thing. Bigger models in this hierarchical sense of nested models will have less bias, but they have more variance, right? So because you have to estimate more parameters, so you generally have less power. So sometimes they'll call, there's all these people have come up with all kind of different versions of these types of models that try to capture departures from Poisson. Negative binomial is one, and that's sometimes called over-dispersed Poisson because there's too many people far out in the tail. There's a way to just modify the Poisson a little differently to make it over-dispersed. There's things called zero-inflated Poisson where you have too many zeros, so it kind of looks like negative binomial. So there's, you can invent a bunch of distributions that try to fit your data better, and that's been done. There's regressions associated with all of them. So just be aware that, count distributions were an active part of research, and there's lots of different options to them, and we'll go over some of them. In general, when in doubt, always fit negative binomial, because it's going to be at least conservative relative to Poisson. But it's not like you give up much because it's estimating just a single other parameter, so it doesn't cut your power that much, and it guarantees your composite intervals won't be smaller than the Poisson, which can be too small. You can do a comparison of models and do something called either a likelihood ratio test. It's not a proper test because you can't test a parameter in the likelihood ratio as boundary, but what you have to do for the dispersion parameter, but gives you some idea of how well they relatively fit to each other, or you could use the AIC. Again, in general, I don't think it's really worth it. Just fitting Poisson, negative binomial should be fine. For you guys, once you fit it, everything is the same. We have the same coefficients. They're modeling the mean typically. You can model the dispersion with covariates. There's generalizations, but generally, usually keep a constant one dispersion parameter, not as a function of the covariates. And the mean model is the same. It's just a log linear model, just like we learned in Poisson. There's nothing new to learn about the interpretation of the coefficients. So it's always nice. Read. And I'm going to stop after this slide, let you out a little bit earlier. I'll for you. We've hit here The same thing we just fit with the HIV wet data. Now we use the negative binomial. It fit. It's this, you have to use this library. I'm sure there's other versions now, but library mass contains it. And it's the glm.nb, so you don't have to put family or anything. It automatically is doing a log linear model of the mean, assuming one dispersion parameter. And everything else is the same, including the offset. Nothing about that changes. And we do get kind of different results. You'll see the standard error changes quite a bit because our original, this data was highly dispersed in the sense that a lot of people had very low events, but some people had really high numbers of events. So negative binomial was a better fit to the data. And you can see that with the p-value, right? It doesn't matter in terms of inference in this case, but it was 0.74, now it's 0.94, which is more realistic. I think we refit. So again, it goes from the standard error, assuming Poisson was 0.08. Negative binomial is almost an order of magnitude bigger, and for highly dispersed data, that's that unlikely, which just shows you how if you're ever fitting Poisson, you really want to check the assumptions because it's really a strong assumption in terms of getting the inference in particular. Maybe the estimates aren't terrible, but the inference. And so here's what I did: a likely erasure test, even though it's not a proper test, because I'm testing the null at the boundary of the parameter space. But you get here's your p-value, 10 to the minus 16. So it's a ridiculously small p-value. It just tells you the negative binomial if it's way better. So NB. Okay, I'll stop here for today. Any questions about this? I think I will skip some over. There's others examples of negative binomial. It's not really central to the course. I think it's useful to learn, so I don't really want to belabor it. So I'll go over a couple of these slides next time, and then we'll start on a new section, which is more central to longitudinal data. All right, have a great weekend. I think just finishing up this negative binomial Poisson number counts were outcome because we reduced repeated binary measures measured over different periods of time on subjects using the HIV wet study. And so we get a count, we get the number of times that they answered the survey. And of course, you need both to get estimates of the rate and the impact of whatever you're looking at. We looked at Poisson regression and point out the Poisson distribution, which is what the inference is based on. It makes a pretty strong assumption. The variance is equal to the mean. And then we generalized, made a slightly weaker assumption, or somewhat fairly weaker assumption with the negative binomial, which just adds one parameter, this dispersion parameter. And we saw that in fact, that does change the inference quite a bit. Standard error changed. It wasn't an order of magnitude, but something like that. So that's not uncommon. And again, the negative binomial can be motivated, the distribution, as a mixture of Poissons, that everybody in the population has their own Poisson, and that there's a certain distribution that assumes about the underlying rates across the population, which is gamma distribution. That's super important, but if you convolve those two, the gamma distribution and the Poisson distribution, you get the negative binomial. Again, not much to learn about the regression part, the coefficient parts. They still have the same interpretation. You're still modeling the mean, which is you can think of as a rate because the outcomes account. And it's a log linear model. Therefore, when you get coefficients, you want to make sure, or you get some combination of coefficients, typically you want to exponentiate them so you get something that's not a log relative mean, but the relative mean. Much like logistic regression like Cox regression that we'll talk about at the end of the course, all these log linear type regressions. And I pointed out that you can think of a test of the Poisson as a test that the dispersion parameter is equal to infinity. As it goes to infinity, or 1 over it goes to 0. That's often how it's phrased, because so you could, it's also that, but that make that obvious. That's under fitting a negative binomial. That's sort of a test of whether the Poisson's sufficient, right? Because the dispersion parameter gets bigger and bigger. The negative binomial looks more and more like the Poisson, which typically means it just doesn't have a big right tail. The counts are much more compactly distributed around the mean. So you can, one thing it's always obvious to do, these I have to, is just to look at the distribution of counts. This is rates, right? Because if I just put counts, that's confounded by the number of observations a person has, right? So I just divide the number of events by the total number of times they filled in the diary in this case, so the amount of time at risk. And this is what you get, and this is very typical of a negative binomial type distribution, where you get often a big peak at 0, and then you get this right tail, so you get events that spread. So a lot of the events are generated by very few people. So like if you count the proportion of people contributing the most of the events and you rank by that, it goes up very steeply and kind of levels off, because the events are clustered in fewer individuals. So that's the classic negative binomial. And we talked a little bit about how that's used in infectious disease modeling. The negative binomial with the big tail implies super spreaders. A few people are doing lots of the secondary infections, and most people have very few secondary infections. And some diseases have that characteristic. I mentioned SARS. Others are much more have very similar numbers of secondary infections. And that information, fitting a negative binomial and that dispersion parameter, can be fed into mathematical models of the disease, which is often done. So it shows how they spread, kind of thing. So it's got a lot of uses. And again, the bottom line is, if you're choosing between them, typically just choose negative binomial. It's a bigger model, so it's going to be less biased in its inference than the Poisson. And you'll just note that there are other options besides negative binomial that try to account for a big 0 peaks. Not so much the tail. The tail, it doesn't count for. There's something called a 0 inflated Poisson. I'm going to post something on it with a little R code. I'm not going to go over it in class because it's not that important, I think. It's just there's a lot of these modifications. So that assumes that your population is a mix of people who have a structural 0, meaning they can't have an event. Let's say you're counting asthma attacks, and some people don't have asthma, right? And you don't know who's who. So you assume there's some portion of the population which can't have an event, those are structural 0s. And then you have the other part of the population that has the probability of a 0, 1, 2, 3, and 4. So it's another kind of mixture model called the 0 inflated Poisson. There's another way people try to model count data. So I'm sure you could have 0 inflated negative binomial as well. I'm sure someone's done that because it's just such an obvious low-hanging fruit. But again, not quite as necessary because that actually models having lots of 0s pretty well. So if I had a distribution that had a lot of 0s but kind of tailed off quickly, that's more like negative, the 0 inflated Poisson. And again, you can get fancy there. Because you've got this probability, the parameter, you add a parameter to the Poisson, which is the probability that you are at risk of any event, and you can start modeling that as a function of covariance, right? Even though it's not measured, you don't know who actually had 0 probability of having any events, but you can use the maximum likelihood and the structure of that to model both how covariates affect the rate if you have a positive probability and how they affect the actual probability that you're in one group versus the other. So that's very much kind of the history of parametric models. Like, you can always tweak them, come up with slightly bigger models, and and then And of course, ultimately, you like something that's more automatic, that could go through a whole spectrum of models and do that, and that's really where machine learning comes in. There is somewhat of a paucity of machine learning algorithms for counts. That's changing a little bit over time. So people tend to do that for binary outcomes. They do it for continuous outcomes. But ones that have these count type of distributions, less so. So that's someplace where somebody needs to make more of these machine learning algorithms that are really take account of the count distributions. But there's not that many. And then I'm not going to go over this. This is for, you can read this on your own. It just goes over another example. It's a census example, so it's not longitudinal. It's just cluster data where you have like county level, and then you have counts of mortality and different, interesting data. It came from a study I think that Jennifer Ahern did a while ago. But I encourage you to look at it, but it's, it just goes through the application of it. There's really nothing new in it. Okay. Yeah.